So in this lecture video, we're going to be talking about buffers. But before we cover buffers, which is weak acids and weak bases with their conjugate bases and salt, I need to make sure that you're aware that there's a list of strong acids and strong bases in your exam reference sheet, which is in page 8 here. All right, strong acids, strong bases. There's also a list of weak acids and weak bases, which are actually here. So anything that has a K and a Kb value is actually a weak acid and a weak base. Now, sulfuric acid is a strong acid. Why? It says large. That means it has no Ka. All right. So any of these things from the hydrogen sulfide ion, all of these bases are actually weak acids and weak bases. So again, if they're not on this list and I give you an acid or base, you should understand that that means to say that it's a weak acid or a weak base. So this brings us to base and acid strength. So strong acids like hydrochloric acid again is a strong acid, and it's a strong acid because in a reaction when I put hydrochloric acid in water, what happens is hydrochloric acid dissociates completely. So it means to say that 100% of hydrogen chloride, in this case ions, or in this case covalent compounds, this compound dissociates completely into hydrogen ions, or what is the name of this again? Hydrogen ions or protons, and the chloride ion. So if I put 10 molar hydrochloric acid, that means to say at the end, all 10 molar is going to split up into hydrogen and the chloride ions. In weak acids and weak bases, all right, only a portion of the acid or a portion of the base dissociates in water. So that means to say that if I give you 10 molar of this, at the end, all 10 molar is not going to split up into the acetate ion or the hydronium ion in this case. Okay, so only a portion of this is going to dissociate. All right, how do you know? Again, you look at your list of acids and bases. That's one way. The other thing that you know that's a weak acid and a weak base is a weak acid and a weak base is always shown by a bidirectional arrow. Okay, now remember, now bidirectional arrows, okay, are actually we've done this before already, are in this case reversible reactions. So these are reversible reactions. Okay, this means to say that here before, if I have 10 molar here, at the end, and we're gonna generalize this is actually not true, at the end of a reaction 100% of this all is gonna turn into the products. There's gonna be no reactants left. All right, in a weak acid or weak base expression, what happens is you're going to have some of this, some of that, some of that. Okay, so you're going to have a mixture of reactants and products, just similarly to like reversible reactions previously. Which brings us to Bronsted-Lowry definition. So Bronsted-Lowry definition before, as you remember, is all about the protons. Okay, and when we talk about protons, the hydronium ion, the hydrogen ions, those are all the same. So we're talking about H pluses or H3O pluses or protons. Okay, so here we have an equation. We have a Bronsted-Lowry acid and a Bronsted-Lowry base. And the reason why I know this is if you look at the product side, water is the one that lost the hydrogen, right? It went from HOH to OH minus. So again, you know for a fact that the species that lost the hydrogen ion is going to become negatively charged, and the species that will gain a hydrogen ion will become positively charged. Okay, so proton donor, base, proton acceptor, okay, base, and then proton donor is going to be the acid. Now here's the deal. Since this is a reversible reaction, what happens is now you have acids and bases and their conjugates. So if I become reversible, that means to say that as the species go towards the product side, some of the species are going to go back towards the reactant side. The reason why this is called a conjugate base is because if I'm going to go back to the reactant side, who is going to be accepting a hydrogen? This guy. Who's going to be donating a hydrogen, which is Bronsted acid? This guy. So that's why the acid and the conjugate base on the product side always belongs together, and the base and the conjugate acid always belongs together. And the reason why we just call them conjugates is because the conjugates are actually on the product side. And if you go the reverse way, this is going to be the base. This is going to be the one that will accept a hydrogen. And this is going to be the one that's going to donate a hydrogen. This is why this is the acid and the base. Going the other way, this is the acid. Why? Because this is the one that's going to be donating a hydrogen. And this is going to be the one that's going to be accepting a hydrogen. Right? So in a weak acid-base reaction, there's always going to be conjugate bases and conjugate acids. Make sure that you understand which one is which. And again, the conjugate base is always going to be negatively charged, right, on the product side, and the conjugate acid is always going to be the positively charged, or becomes more positively charged on the product side. All right. So this is an example of a weak acid equilibria of hydrofluoric acid. Hydrofluoric acid is a weak acid because A, it is not on the list of strong acids. B, it also has a Ka value. All right. So the amount of products and bases can be, in this case, can be expressed as an equilibrium expression, Ka. Ka, remember we already talked about KeQ before, okay? Kc, all right, all of that stuff. This is an equilibrium expression. That means to say at equilibrium, you're going to have a mixture of products over reactants. Similarly, one of the things that you have to understand is water is always omitted from the equation. Why? Because water, anything that is a pure liquid or a pure solid, and obviously water is a pure liquid, is always omitted from an equilibrium expression. Okay, so the Ka of hydrofluoric acid is 7.4 times 10 to the negative 4, which is 0.00074. Now again, that means to say that there is going to be more reactants than products. And if I write this as an expression, actually as a, I hope that you understand this, it's actually 74 divided by 1, 2, 3, 4. So it's going to be divided by 10,000. So that means to say for every 74 products, you actually have 10,000 reactants. All right. So that means to say that obviously there's more reactants than products in this case. And the reason why that comes again is because this is a very weak acid. So only a portion of the hydrofluoric acid is going to dissociate into the hydronium ion and its base in this case, all right, or its negative ion, all right? So just know that you can express all of the equilibria, all right, is actually in your, again, in your exam reference sheets, Kas and Kbs. All right, this is going to be similar for the weak base equilibria of anything, like ammonium is going to have a Kb. The only reason why it's called Kb and not Ka is because it's the equilibrium expression of a base, whereas this is the equilibrium expression of an acid. Okay, now why is this very, very important? Because this is how you create buffer. So the way you create buffer is you have a weak acid, so hydrofluoric acid is a weak acid, and you treat it with a strong base, or vice versa. You get a weak base and you treat it with a strong acid. Here's the rule. You cannot, in this case, add equimolar, meaning to say the same molarity or the same normality of a strong base with a weak acid. Because as we remembered before on our previous acid lectures, if you treat, like if I have a 10 normal weak acid and a 10 normal strong base, what is the actual pH of the solution? The pH of the solution, folks, is going to be greater than 7. And this is basically going to be eliminated from this equation, okay? So you cannot have that. The magic ratio here is always going to be a 2-to-1 ratio. You always want to have 10 to 5 is the same as 2-to-1, okay? All right, 20 to 10, that's a 2-to-1 ratio. 100 to 50, you guys get the gist, okay? So that is actually the way, that's actually how you would mix a weak acid and a strong base, or a weak base with a strong acid. It's always a 2-to-1 ratio. The weak acid or the weak base always has to be, the optimal concentration always has to be twice as much in equimolar concentrations. Okay? I hope this makes sense. If this doesn't make sense, please ask these questions during class. So this is an example of how you make a buffer. You get 100 mils of a 0.1 molar acetic acid, weak acid. It's mixed with 50 mils of 0.1 molar sodium hydroxide, strong base. If we do the normality, as you can see, the normality of the acid is 10. The normality of the base is 5. So this follows the 2 of the weak acid to 1 of the strong base ratio. And we can write this reaction. So we have 10 normal here, we add 5 normal. This is a limiting reactant problem now. And since this is less than that, this is going to be the limiting reactant. Okay, so this is going to be what's going to drive the equation. Since this is the smaller amount, this is going to determine how much of the products we actually create. Okay, so if we have 5 normal sodium hydroxide, we're going to have 5 normal sodium acetate and 5 normal water. And again, water in this case is always going to be a spectator ion. We never write this guy. Okay, so this is actually, if you want to think, this is actually inconsequential for you. What happens, however, is since this is 10 normal acetic acid, there's going to be excess of this. All right, so since at excess, hypothetically speaking, 5 of this is going to be used, so that therefore at equilibrium you actually have 5 normality left. So at equilibrium, remember products over reactants, you're going to have 5 normal of this and 5 normal of this. Now, what happens here? What happens at equilibrium? Ladies and gentlemen, there is no sodium hydroxide ion left. Why? This is the limiting reactant. So you have 0 of that. So what is the ratio between the conjugate base and the acid? It's 1, 5 to 5. All right, and again, obviously this is all used up. At the end, there's limiting reactant is always going to be used up. Excess reactant is going to be left over. All right, and obviously, I hope that this makes a lot of sense again. So again, this is how you make a buffer solution. The best way for you to get a buffer solution again is if you treat the weak acid or the weak base with half the molarity of the strong acid or the strong base, which is this case. And the reason why that is because you have no strong base and, you know, in this case, left over. Now, why is this very important? This is actually how it shows you actually what is the reason. So this is actually the previous, okay, reaction now. Now we have 5 normal sodium acetate, 5 normal acetic acid, which can be shown here. The Na is not shown because it's a spectator ion. Okay, so this is actually CH3CaO minus Na plus. So we have equal amounts of acetate of acetic acid and the acetate ion. So what happens is, since you have equal amounts in a buffer solution, what happens is if you add hydroxide ions, the hydroxide ions, okay, right? What happens? Look at this one. The hydroxide ion is going to react with the acid. So therefore, the effect of the added hydroxide ions is minimized. If we add an acid, it's going to react with the base. The base in this case is this. Remember, this is the acid. This is the conjugate base. All right, so if you add hydroxide ions, it reacts with the acid. If you add hydronium ions, it reacts with the base. All right, and because of that, that's why it's called a buffer. It's because it buffers the effect of extra additions of acids and bases. Obviously, there is an N, okay? So this is Le Chatelier's principle again, right? Just like removing, right? So if you remove, if you add this, if you add acids, it's gonna shift the other way. If you add base, this is the same as removing this, it's gonna shift the opposite way. So this is actually following Le Chatelier's principle. All right, so this, I hope this makes sense. Now there's going to be a point in which the buffering effect of a weak acid or weak base and its conjugate is no longer going to be effective. This actually shows you. All right, so as you can see, you can keep adding up to almost 100 milliliters of 0.10 mole of sodium hydroxide to this buffer solution. All right, but as you can see, I add from 0. If I add from 10 to 90, the effect on the pH of this buffer solution is actually very, very good, right? It doesn't have this high fluctuations in acid and base like in the pH. That's why it's called a buffer, because again, it can take excessive, well, not excessive, but large amounts of either an acid or base. But eventually, there's going to be a point in which that buffering system is going to be overwhelmed if you add too much acids and too much bases. This is actually the same way as you have in your body. This is actually the carbonic acid buffer solution, which we're going to talk about later.